So yeah, as the title suggests, I'm going to talk to you about prawns and probabilities, specifically about an experiment that we've been doing in Uppsala for the last year, looking at how we can match models of collective animal behaviour which have existed in quite a well-developed form for the last 10 to 15 years with much of the empirical data we've been collecting for perhaps only 5 to 10 years, which is based on video analysis and tracking data from animals. So a lot of work has gone on in the past on understanding how animals interact together and how they produce complex group behaviour. But that's usually been done by simulating proposed models and seeing if that behaviour looks realistic. What we really want to do is say, from all these models that we have, can we use real data now to say which models are correct, which ones should be improved, and where future models should go. So I'm just going to try and make sure we're all on the same page about the sort of phenomenon we're talking about here. So I've got a couple of videos to play here. This is a group of starlings in Italy, and you may well have heard about some of this research looking at rules of interaction between starlings and flocks. You can see here we have a flock of several hundred starlings moving around in a very complicated manner. And there's obviously a lot of complex behaviour which emerges from the group that wouldn't exist if you only had a couple of starlings together. And information travels through that group very quickly, such that if there's a change in direction on one side of the group, the whole group quickly changes its direction. You get large-scale density fluctuations. And when we talk about collective behaviour, what we're not talking about is just animals doing their normal thing together, but they happen to be in the same place. We're talking about group dynamics that are far more complicated and on far larger spatial scales than a single animal or a couple of animals can do on their own. And if we move to the next slide, we can sort of see this in a slightly more quantitative viewpoint, because we've got an experiment in the lab, which is admittedly far less glamorous than the starling experiment. But here we have an experiment involving some locusts, which was published in Science in 2006 by Ballerina Town. On the right, we have the experimental setups. You can see we have a video still here of a ring where locusts move around in an essentially one-dimensional environment, sort of following each other around this ring. And the center here is occluded so that they can't move through the center. And you get a distinct phase transition as you change the number of locusts in that experiment. So in the top left, you see the behavior you get if there are only 5 to 10 locusts in that experiment. On the left-hand side here, we've plotted the total amount of alignment going from -1 to 1, indicating either every locust is traveling anti-clockwise or every locust is traveling clockwise. And although there are periods during this experiment where the locusts are all traveling clockwise or anti-clockwise together, they always go back to the center, to a disorganized state where many are traveling in different directions at a time. In contrast, if we move up to, say, 10 to 20 locusts, we get this intermediate behavior in panel B, where you have either complete clockwise motion or complete anti-clockwise motion, and very sudden shifts between them. So what will have happened here is that one locust will have randomly changed its direction free from the rest of the group. And then that change will get propagated throughout the rest of the group until everyone switches to the new direction. And obviously most of the time when that locust switches, it'll be pushed back to its previous direction. But just once in a while, it's able to propagate its own information through the entire group. And it gets harder and harder for that random locust to do that as you move to bigger and bigger group sizes. So by the time we get to a group size in the order of 50 locusts, we have completely coherent behavior, where for the length of the experiment, all the locusts rapidly choose a single direction and then stick to it. And you can see this fuzziness here is random switches of direction by 1 or maybe 2 locusts, which are then quickly eliminated as they come to face the rest of the group. And we suppose that most of these phenomena can be generated by the animals obeying quite simple local rules. So the one thing we try and avoid is the notion that the animal can have any concept of what the entire group is doing. If you look at those starlings, it's very unlikely, especially in the midst of the flock, the starling can alter its behavior in some sort of coherent way that it wants to create a particular kind of group structure. Instead, it's likely that these animals respond to their local neighbours in quite fixed, preordained ways. It's only this multitude of interactions that eventually produces complex behavior on the scale of the group. And this is a very sort of canonical example of the sort of interactions we presuppose. On the left, we have a diagram that shows a focal animal in the center, and around it there's a zone of repulsion, a zone of orientation and a zone of alignment, sorry, a zone of attraction. So if our focal animal here is confronted by anyone in its zone of repulsion, it will simply move away from them in an effort to retain its own, I guess, personal space. Within the orientation zone, it will try and look at all the animals within that orientation zone and match its own movement vector to them. And in the attraction zone, this allows the animals to actually conglomerate in the first place, which then gives them the sort of density needed to create this complex behaviour. And while this is a canonical example, there's currently a lot of debate about exactly which of these forces are needed. So especially between orientation and attraction, there's been some recent papers both arguing that only attraction is needed and some arguing that only orientation is needed. And this is one of the reasons why it's absolutely crucial to do this fine-scale analysis in a Behaviour manner, because we can avoid overfitting. If you have a zone of attraction and a zone of orientation, you will inevitably be able to fit your data just as well as one that includes only one of them. But if you do a Bayesian analysis, we can say, well, how certain are we about the particular values of the parameters associated with these zones? So each zone will have a size and a force strength associated with it. And if those aren't well defined by the data, then we can't support the idea that those forces are actually there. And I don't know, maybe some of you will see analogs here between this and something like a magnetic gas. In a magnetic gas, you have particles which have a magnetic spin, and when they come close to other particles, they will try and line up their spins, or, well, maybe that sounds a bit too conscious, but they will line up their spins in order to minimize energy. And it's very similar to what goes on here, except that the particles have two properties that a standard physical system wouldn't have. Firstly, they self-regulate, principally in speed. So we assume they attempt to keep their own speed roughly constant. And also, that magnetic spin, rather than simply being a property that leads to a global magnetism, actually then defines the future behavior of the particle itself. So it travels along the direction of its spin. So on the right-hand side, you can see the sort of behaviors we get out of a model like this. We have random groups that just sort of clump together but then have no coherent behavior. We get rotational groups, which are a very common feature of most of these models. So this is very similar to something like the school of fish you might have seen in a nature documentary. And then we get various kinds of completely aligned groups that travel quickly in a single direction together. Going back to the Starling experiment, people are starting to try and look at this fine-scale data to learn rules directly by looking at the positions and movements of the individual animals, rather than looking at simulations of the system and saying whether that looks realistic or not. This is, I guess, would be called a seminal paper from 2008 by Ballerina Town. You may well have heard about this in the news. This is the one that says that starlings interact with their 7 nearest neighbours. And that particular number is very suspicious, since it was done using this analysis on the right. Basically here, they plotted, if this is the focal animal in the centre and this is the directions around it, they plotted the position on average of its nearest neighbour. And it's generally either in front, behind, or to the side. And they do this for each nearest neighbour until we get to the 10th nearest neighbour here. You see here there's very little pattern at all. And they measure the anisotropy of these particular figures and then say, okay, well that's become insignificant by the 7th nearest neighbour, so the animal is interacting with 7 neighbours. However, of course, if I was to interact with only one neighbour, and then he was to interact with only one neighbour on his side as well, I'd still end up being quite correlated with my 2nd nearest neighbour. So correlations like this can be very weak evidence for particular values of parameters, but they can start to give us some idea of the sort of structures of interactions we might hope to find. So coming to our experiment, I was going to show you a video of this, but you'll see a clip of it later, but it's sufficiently boring that I don't really want you to doze off in the middle of it. But the picture on the top left sort of describes the experiment we have. We have 6 prawns in this picture, which move around in a ring similar to those locusts. And here we just have in red the ones that are moving clockwise, in blue the ones that are moving anti-clockwise. And here's a few metrics about that, the empirical data we recorded. So this is averaged over all experiments with 6 prawns. This is the number of prawns traveling clockwise. And you see they start off mostly in random configurations defined by a binomial distribution. Most experiments have 3, 4, or 2 prawns moving clockwise. And rapidly they move to a state where almost all experiments have either 0 or 6 clockwise moving prawns. So there's been clear alignment. And this graph here is essentially the end of this one plotted, but for 3, 6, and 12 prawn experiments. You can see in all experiments, alignment is found. And here we have the total amount of polarization adjusted by the amount you would expect at random. And you see that 12 prawns align more strongly than 6, which align more strongly than 3. So this is the sort of behavior that any respectable model for this system has to replicate. So what sort of models might we actually investigate? Well, there's the first sort of standard model of one-dimensional collective motion introduced Shirok in 1999. And in that experiment, each animal has some zone of interaction. It averages the directions of the other animals within that zone, and then adds some noise to that, takes the sign of it, and then moves in that direction. Equivalently, but maybe easier to frame, in a recent paper by Behaviour in 2010, the animal simply takes the direction of its local the average direction of its local neighbours with one probability, or the opposite direction with another probability. And here, prob P would be much greater than a half, so on average you would tend to follow your neighbours. And the model we're going to talk about now is that you tend to just carry on whatever direction you're already going, unless you choose to make a change of direction with probability P, which then depends on the directions and positions of your neighbours. And to go through in a bit more detail the specific kinds of models that we've actually investigated. But what we're doing here is selecting models by the marginal likelihood or evidence. So in all of these models, which have different numbers of parameters, it's very important to note that we've integrated out those parameters, so these are fair comparisons. So although these models are actually more complicated than these ones, these are fairly judged to be better, rather than just being fit in the data better. So we start off with a null model, which just says prawns change direction at random. They don't interact with each other. This is all due to just random noise. And also you can see it performed very badly compared to the other models, as we would hope. But it gives us a baseline from which to judge the sort of scale of model evidence we expect. We then move to a mean field model, which produces very good simulations of the data, which is yet another reason to be suspicious of simulated results, because this model only says, me as the focal prawn, I interact with my neighbours around the entire tank. All I care about is the average direction of the other prawns within the tank. So essentially, my interaction zone spreads through a whole 2 pi of the ring, which is pretty unrealistic for a prawn that lives in a muddy environment and has barely any eyesight and antennae that are only maybe 5 degrees long within that tank. But produces very good simulations, so it considers a new baseline and a topological model, which is one where you interact with a fixed number of nearest neighbours, actually performs worse than that. So adding that extra complexity of having to choose a particular number of nearest neighbours to interact with gives us no added benefit on the mean field model. However, models that we might consider to be more realistic, spatial models where the prawn interacts with other prawns within a particular fixed spatial zone, do outperform these, thankfully, in predicting the fine scale data. And these are all variations on theme. We have different types of interaction zone. Here we have symmetric and forward orientated, where the prawn interacts with others that are coming towards it. And here we have symmetric and forward orientated zones, where it interacts with both prawns coming towards it and prawns traveling in the same direction. And so at this moment, we would say, well, I think the prawn has a forward-orientated interaction zone and only interacts with its neighbours that happen to be travelling in the opposite direction. And we would think that this would probably give us something reasonably realistic. And in fact, it should be noted that apart from the null model, every single one of these models can give you realistic simulated behaviour if you choose the parameters correctly. So this would basically just be the models due to Abaid and Girok and various other people who've studied this sort of one-dimensional system. However, you may wonder why we have black and, oh, I'm supposed to be going through these models, so let's flip through. You may wonder why we have a black and grey dots and why half this graph appears to be missing. So we have our optimal model, but we seem to be missing something. Well, the reason we have grey and black dots is because there's a huge problem with what we've chosen as the optimal model, which is that it doesn't produce the simulated behaviour that we would expect. So if we take either the maximum a posteriori or the mean a posteriori parameters from that, and they're quite well defined, so there's very little uncertainty in them. And then we simulate experiments based on that interaction. Here's the empirical data we saw before, and here's the results of our simulation. See, there's no significant alignment at all, and there's nothing happening in 12, 6, or 3. This is on a far smaller scale. I should have plotted this on the same scales, but this is up to 0.2, this is up to 0.8. But you can see very clearly here that they all remain in this random binomial state. So what's happening is we're getting a model that does better than any of the others we've looked at and predicting exactly what will happen when you look at the prawns, just a pair or 2 or 3 of them together on a small scale. But on the larger scale, it just doesn't give us the right sort of behavior. And so one of the reasons I subtitled this talk an adventure in learning collective animal models is because at this point I was practically on my hands and knees wondering what the hell I'd done wrong and why God hated me. So after struggling with this for about 3 or 4 months, one of my co-authors called Roman had an idea on exactly how we might be able to fix this. And we'll see this in an example of a turn on the video in a minute. This is the sort of interaction we've been proposing so far. 2 prawns meet, there's an interaction zone around one there. When the other one is in its interaction zone, its probability of changing direction goes up, then it goes past, and the probability of changing direction goes down. And this is what every single model of one-dimensional movement has assumed. But if we look at the natural video of how this turn occurs, you'll see just how noisy and specifically not smooth and Markovian this is. So you see a few prawns sort of moving around here. And I've selected probably the most exciting 10 seconds of this entire thing. So you saw there, one prawn went past another, and then a few seconds later it decided, oh, I'm going to change direction. So its decision was not predicated on where its neighbor was now, but on the interaction that happened just before. So in light of that, we propose a non-Markovian interaction where, again, my probability of changing direction is increased when I interact, but then it remains raised for some duration afterwards. And that's obviously another parameter that we need to learn, another element of complexity in the model. But we find that adding that in gives us, well, firstly, a boost in the model evidence based on the fine-scale data, which is nice. So we've already taken that these 2 models are better than the spatial ones we've decided on before. You can see now on the legend what these grey and black dots were. Black dots are ones that were inconsistent when simulated in terms of the large-scale behavior. And you probably can't see under this red, but these 2 are grey. These are our best 2 models. Technically, this is our best model here, but I've highlighted both because it will lead me to discuss something about the closeness of fit on the large scale. But all 4 of these are now outperforming our previous optimum, so we can quite reliably say that these are better, and we can then hope and pray and finally see that they do have alignment within them. So this is our truly optimal model according to the evidence on the fine scale, and this is the second one I highlighted. These are now aligning to roughly the correct level of polarization for the different groups. Particularly this one on the right looks almost perfect in the degree of alignment and the speed of alignment. This one on the left looks a bit more murky up here, but you can see quite clearly that it does align. And what's really happening here is rather than just having everything in 0 and 1, you get a few experiments that stay with 1 or 5 clockwise moving prawns. But importantly, they've moved away from that central binomial distribution and instead have now got this sort of large-scale agreement with our experiments. So at the moment, this is where the experiment sort of stands. We've got model evidence on the fine scale, which allows us to judge quantitatively which model is better. We can use the full array of Bayesian methodology to incorporate all our uncertainty to say this model, despite its added complexity, is better than this model, or in this case, this extra parameter isn't worth including. What I'd really like to do is bring that to this large-scale level as well. So here, at the moment, what we've got is it consistent or is it inconsistent? But as you can see, this one, while it had a slightly lower marginal likelihood, is more consistent, we would think, here than the one on the left with the original empirical data. So what we'd really like is some sort of probabilistic measure of closeness of fit on the large scale. Now we could measure something like the KL divergence or the distance between a number of statistical metrics, and then just say, okay, well, let's choose some way of assigning a probability based on that distance. But if we just do that arbitrarily, it's then saying, well, we have to choose ourselves a weighting between large scale and small scale fit. Which one is more important to us? And I think it would be much nicer if we could find some logical reason to say that this is the amount of variation we expect on the large scale versus small scale. But that's sort of for the future. What I'd really like you to take away from this talk is the principal message that there have been all these simple models of animal behavior, and most of them have an enormous amount of overlap. In fact, that's something I meant to talk about, didn't quite hit on, which is most of these models display largely similar modes of behavior. So, for example, in that original slide we saw, the model could make a rotating group of particles. You see that in practically every single model of 2- or 3-dimensional group behavior. So it's impossible to just look at the large scale and say, well, that's obviously this model, because all models can produce most different kinds of behavior. Furthermore, although they can produce the right sort of large-scale behavior, they get the details wrong. As we saw in the prawns, we had an array of models that could all produce the right sort of large-scale behavior, but when we had to use the parameters that we judged from the fine scale, they could no longer reproduce the large scale. So something between the details and the large scale has gone wrong. So the standard models do show us a lot about what is essential to get coherent group behavior, the sort of feedback loops we need, and the simplicity of rules that are necessary just to reproduce behavior. But if we actually want to know exactly what interaction rules an animal uses, then we have to look at the details, and we have to formulate more complicated models. And we do want to do that because often in biology, it's the details that matter for certain questions. So we may well want to know, for example, do all animals evolve the same sort of rules? Is there some sort of convergent evolution to an optimal set of rules that are somehow easy to memorize for the animals? Or do animals simply play around with rules until they find one that works and then fix on it such that different species would have different rules? Also, if we want to know, if we look at things like orientation and attraction, especially if it turns out that attraction is by far the most important force, we may start to hypothesize, well, maybe it's the need to come together was the primary force, such as safety in numbers against predators, and the ability to behave collectively in such complex ways was sort of a nice byproduct of that original urge for safety. So, in evolutionary terms, there's a lot of interest in the details of the model. What I think this crowd should really take away is the fact that we have this vast amount of data now. Animal experiments used to be judged on the basis of maybe 3 or 4 metrics at a time. People would painstakingly get a pair of binoculars and watch where a pigeon had gone over the horizon, or time it on a stopwatch until it got home. Now we stick a GPS track on the back of a pigeon, and when it comes back, we've got 2,000 seconds worth of data we can analyze. And as soon as we get that, we have a sort of treasure trove of data with hidden patterns in, and which we can start modeling using data mining techniques on deconstructing in various smart ways, which, to be frank, most biologists won't be able to do. So if you're looking for some low-hanging fruit or some large sets of data that you can analyze, well, you know where to go and find it. So that's all from me, so thanks very much.
Questions? So, did you apply this to the birds as well?
I haven't applied. The only true data I've applied this to is the prawns. Okay. So I have another paper I've just recently published. I think it's in press at the moment. It's based on how you do this for just groups in general. But that's all sort of predicated on if you already sort of know what the basic model you're looking at is. So one thing is, I mean, sadly the people with the Starling data apply the text of it, so I haven't applied it to that yet.
Well, the reason I asked was because I was thinking when you were talking about the prawns, and it seemed like, you know, even though that's moved past one of the prawns, it kind of turns around and remembers, and you were talking about a timing. And I was wondering if it had more to do with, you know, for instance, birds are visual, so if they go past it, it's such as they're out of their zone, you know, whereas a prawn, I would imagine, probably deals with vibrations in the water or something like that, as opposed to vision.
It's a good point, because the interaction zones here were generally on the order of the size of the prawn. So it looks like interaction takes place basically by contact. And also, yes, the birds would probably provide a better set of data for using traditional models, because a bird can't really afford to wait quite in the same way in order to react, because they have to keep moving. Like these prawns, the reason I didn't show a full video is because they tend to just sit there for a while and not really know what they're doing. And their collisions are often of the form they collide into each other, one swims away, and then a minute later this guy goes, oh, maybe I should follow him. So we have applied some of this to fish, and it seems the standard model seems to work a bit better there. Like so the fish, the lag between interactions seems to be a lot smaller in fish.
Next question.
In comparing the performance of the models, you said you used the log likelihood after integrating the nuisance parameters. But does your conclusion change if you had used BIC, Basic Information Covariant, for example?
Yeah, sorry. It was asking if instead of integrating out the parameters in the fully Bayesian way, if I just fitted it with maximum likelihood and then used something like Bayesian information criteria, or I guess AIC equally. It's not something I've done, principally because if I can integrate out the parameters, it seems there's no need to use an approximation like BIC. To my mind, anytime I've tried to use BIC, it's never really worked very well. It tends to have a ridiculously large penalty on parameters, so I always end up with a null model or something. AIC I have used before in other contexts, and it's worked much more nicely, but since that's something I'd only really consider if I couldn't integrate out the parameters directly.
Richard, you talked 2 years ago in Oxford about pigeons, and now you've talked about prawns. I was wondering if you'd thought about what you could do if you had a larger scale experiment where instead of having prawns in this annular confinement, you maybe had cats.
I don't work with animals that don't start with pig.
Okay, pussy cats.
I believe cats are reasonably well known as pretty antisocial animals, so I doubt they'd display anything too complicated in their social interactions.
Okay, I'm trying to embarrass you a little bit. The serious point following that is that I was completely shocked when I first read Jared Diamond's book, Guns, Germs and Steel, in which he partly explains, well, talks about a lot of things, but he explains that people around the world, different parts of the world, have reached various stages of development for various sorts of reasons, including their geology and geography and so forth. But as an Australian, I notice particularly makes the point that if you're not in a part of the world where a native animal, one or more native animals, are what he calls herdable, you have a great deal of trouble domesticating them. Now, you know, we all know the term cat herders are people who can do difficult things because they're hard to herd cats. Well, in Australia we have kangaroo herders. Okay, if you put a bunch of kangaroos in a paddock, they do not all clump together, they do not all run around. Whereas if you put a bunch of sheep, which of course are not native to Australia, you know, one man on horseback and 2 clever dogs can control 10,000 sheep with minimal effort to put them anywhere you like. So just wondering whether it would be interesting to think about parameterising different animals in terms of their herdability.
Well, so in fact, you sort of touch obliquely on a very interesting point which we've been discussing in the community recently, which is, I mean, for example, these prawns are not fantastically well-known examples of social animals. No one puts them on nature documentaries, or you never see David Attenborough talking about some mud-water prawn. So one thing people have started to think of is how much of what we actually observe in a sort of contrived environment like this is real social behaviour, and how much is it just true that if you can find any sort of animals that have the barest amount of tendency to come together in a reasonably confined environment like a ring, is it true that they will always end up going around in the same direction or displaying some sort of coherent behaviour just by the confinement of the environment? And that's been quite a big worry, as I say, with stuff like this. The idea, certainly one of my collaborators has questioned what he called the ecological relevance of studying prawns that basically swim around on the bottom of muddy streams and are only found in the same place because there happens to be food in the same place. So this is one reason why a lot of the research gets done on fish, because then you actually do see these large-scale sort of schools in open water when they're not forced together by anything other than their actual social instincts.
I was wondering if your models could improve if you make the tendency of these animals to be repelled or attracted toward each other, depending on whether they're male or female.
That's almost certainly true, and I think people have done some experiments, not quite so quantitatively as this, but they've done experiments where you put, say, a female usually in a largely male environment, and surprise, surprise, you get a lot of the animals will be following the female around. So what we're trying to do here really is build it up from the most basic things, and in fact, I'm not sure anyone knows which ones whether these were male or female. But definitely, if you had certainly maybe a more developed species or certainly a more complicated model, you could, in a wider space. For example, if you were looking at herding sheep or something like this, you definitely would expect to see something along those lines.
Next question.
I have a technical question. I didn't quite catch what are the cues that they actually use in order to determine the behavior, and if you have any idea of what would be the memory that they actually use in generating subsequent behavior. As opposed to the the same
Do you mean how they operate the memory or how long the memory is?
Yeah, something like that. And then what are the cues?
So we don't know exactly how they follow their neighbours, whether it's visual or touch, but the evidence we have from this suggests that it's based on contact, because we track an element roughly in the centre of the prawn, and then the zone of interaction extends roughly to their tail and their head, or the end of their antennae. So it seems like they're mostly interacting via contact, which makes sense because these are prawns that live in very muddy water, so they would usually do everything by touch. The memory...
It's directional? It's directional? They have two antennas?
They do have two antennae.
So
but
which one touches, you get some kind of direction information?
Well, it's my suspicion on this is it's more that they just sense something sort of go past them, because the interaction seems to last as they go behind as well. In terms of memory, the length of the memory is on the order of a few seconds. For the mechanism of memory, I really have no idea. I mean, it could be something, it's something that's simple. It's unlikely to be really cognitive on any great level. It could be something as simple as when they're sort of hit by something coming the other way, it somehow raises some sort of hormonal level, which then decays away. But I'm not really in a position to speculate too much about that.
Thank you. Any other questions? Well, this was a very interesting session, very good talks, and you can also tell by the responses. So let's thank our speakers.